So it's basically solving session. We'll talk about the exam, some exercises we did in the exam you may need me to go with you
دكتور
on, and
ماشي
we will solve other exercises as well.
مش ساتردي في تي ار
I don't know. I'm having solving session. For those who care about, they can come. Those who are not
اوكي
caring about, it's up to you. It will be recorded so you can, but you don't profit from, in this case, from feedback questions. So in case you have a direct question, you answer. It's your time to go and look for answers. Like if you have a specific question, but don't come later. Tell me I have a question regarding the solving session. No, solving session
يس
you'll be in class if you have any question related to it. Yeah. So today I'll be doing the PID, Star PID controller, and tomorrow 6 p.m. solving session regarding the exam and other interesting things. So in controller design, usually we start by control requirements, then design by pole placement. So you convert this requirement to pole location. Then we do design by pole placement, we call it. Okay. Then we'll give you an introduction at the end to PID control. Let's start with control requirement. Usually approach to control design translate engineering specifications into control requirements. Okay. Then you design a controller to meet those specifications. What are those specifications? You have the transient specification and the steady state specification, and you know all of them. So you find me going quickly. You know all of them. Transient specification are tau, which is their time constant, overshoot, rise time, settling time, peak time. All of those are transient specification. And the steady state specification are the steady state error. Basically what you can find using final value theorem or using system types, and you directly can predict the steady state. So then those are your design requirements. As in your project, if you had a look on your model, if you had a look for the project of model, I was yes, you have of course the project from the beginning of the term, and now I give you a short illustration about the project so you can go and see my illustration about the project. But yes, here in the project I'm asking you to design a controller based on some design requirement. So you have design requirement. My design requirement as I want you to design a controller for a steady state error less than 0.01, for a maximum overshoot less than 5 or less than 15%. Also I have a design requirement like a settling time less than 10 seconds or less than 5 seconds in a different scenario. Okay, so those are design requirements. You need to translate them to pole placement and then design your controller. Good. Of course I put for you like here the project submission and the deadline and the project description. Okay, so the project description you can find also on the playlist you have. Okay, so you have the playlist, you can see the description about the project. Any question you will go back to me. So then now how to translate the design requirement transient and steady state to pole placement. We know that poles of a system affect the time response. The pole location affects the time response. We've spent some time on it, right? Choose controller gains. Our goal in control design to choose the controller gains so that poles of the closed loop system meet your requirements. Because if your requirement having this settling time, this overshoot and so on, so then you need to ask the question where I need to put the closed loop pole to achieve this requirement. So once you choose the poles, then you choose the parameters for your controller, KP, KI, and KD. If system is simple, like first order or second order system, it's easy doing using algebra. We'll see in examples using system identification algebra, we can find KB, KI, KD. But if the system is complex, so we need to use, like if the system higher order system with zero, uh, you can still approximate it to a first or second order system if it's possible. So you can see the dominant poles and approximate it to the slower poles and neglect the faster pole. So then if you can still able to approximate your higher order system to first or second order system, then yes, you can design a controller KPKI KD using some algebra system identification, like by hand calculation. If you cannot, so then we need to use more advanced technique like root locks or body plot. So we'll see how time permits, so we can cover as much as we can from those two techniques later on. But you know, you can still design your controller using simile, just auto tune whatever order of the system is, you can do it. Okay, but now we'll learn how to do it by like using hand. Actually, how MATLAB is doing this calculation. Okay, later on when we understand root locus and body diagram, we see also understand better how MATLAB is doing this calculation when you click tuning. How MATLAB is doing this calculation for higher order system if you have like using root locus method or body diagram method. Process is generally iterative because why iterative? Because if the system is higher order system and you approximate it, you may don't really have the exact system. So then I'm saying iterative because you find your KP, KI, KD and you go and you plot your response, you find you didn't really achieve your requirement. Settling time requirement, for example, was 2 seconds, but you have 2.5 seconds. What the controller you designed gave you a settling time of 2.5 seconds. Then you need to retune the PID parameter to make sure you satisfy the requirement. That's why I'm saying here it is generally iterative. So make sure after designing, look to the response and verify that after finding your controller, look to the response and see if you are satisfying your requirement or not. If not, means you still need to tune your parameters. And I need to see plots in your project showing me like you are satisfying your requirement. Okay. Um, so here they go over example. Uh, how to find my.
I can learn to understand.
Okay. Find the closed loop transfer function for the cruise control system with PI controller. If you wish, you can copy the image and go to the whiteboard and try to work on. Good. Um, okay, so create new whiteboard. So they said find the closed loop transfer function. Is it something able to do? Closed loop transfer function, then it is V, I need to do it this way, V over V desired. Okay, V over V desired equal, can you help me? V of S
Yeah.
over V desired equal to, yes, go ahead. V over V
Yes,
desired,
doctor.
yes,
We multiply Kp plus Ki 1 over L 1 over S multiplied by 1 over Ms plus V.
yeah, thank you, Tariq. So
تاني forward على 1 minus 1 plus loop.
Over 1 plus the numerator.
okay, so this is the which, yeah, as Rami said, this is the forward over 1 plus loop, right? So now you know it. Okay, you can do it. It's not really hard, right? And so here the question is asking you to find the closed loop transfer function for a cruise control system. Let's say cruise control, we know it's a first order system with PI controller. Okay, so you get the final answer. Okay, so this is your answer. Then with two parameters Kp and Ki, can place poles of this second order system anywhere we like. 2 degree of freedom. Okay, this is, I don't want to talk about it now. Later on we'll see more clear things. So I'll keep going forward. Basically what we are doing is system identification, if you want, but later on we'll see better examples. Okay, so taking mass equal to 5, arbitrary saying like b equal to 1, and then they're asking you to choose Kp and Ki to achieve a settling time of 2 seconds and peak time of 1 second. Okay, so uh, they want you want to find Kp. This is my closed loop transfer function, of course. We over there. Find Kp and Ki in order to
Doctor?
achieve settling time of 2 seconds. Yes, Tariq, and peak time of 1 second. You have question?
Yes, doctor. إذا بحط الترانسفير فانكشن اللي فوق على الماتلاب وبكتب له كوماند سمبليفاي بيعمل لي سمبليفاي لها ولا لا؟
But you need to define your as sys. You need to define them as symbol, and I think, yeah, they do. MATLAB they able to do.
اوكي.
So settling time equal 2 seconds and peak time equal 1 second. Those are my design requirements. I need to design a controller to achieve a settling time of 2 seconds and peak time of 1 second. Okay, then how to relate this to pole placement and to KPKI at the end? Well, settling time, I know it's equal to 4 over zeta omega n. But this I want you to pay attention here. This is only valid for a second order system. You remember we was only talking about a basic form of second order system, omega n square, even we don't put k, over s2 plus 2 zeta omega ns plus omega n square. So this is valid for this basic form. There is no zero in the denominator. Here you have zero in the denominator. So I was talking about a canonical system, a second order canonical system. This is not valid for uh, settling time equal 4 over zeta is not valid for non-canonical system. And peak time equal pi over omega d, also the same is for canonical second order system. From this 2 I can find omega d, and I know omega d equal to omega n 1 minus zeta square. So I have omega d, so, and here I have a relation between zeta omega n, and here relation between zeta omega n. So two equations with two unknown. I can find zeta and omega n. Right? You can find your zeta and omega n from these two design requirements. So that's what I'm doing. First, I'm looking to my design requirement, then find the zeta omega n, and this is my basic form. So what I will do now, I'll be comparing this to the denominator of my closed loop transfer function. This is as far as first order approximation, it's alright. I'm assuming like I have no zero in the denominator. But this doesn't really work. So this kind of system, the example Prof Hill gave, is not really, like, I would say, like, we don't take now. This is more if you have using root locus method, you can use this kind of equation because you have zeros, so you're able to deal with zeros and higher order system. But it's still always as first order approximation, we can compare just both denominator. So then comparing both of them, you'll be able, let me have this in the general form. So in the general form, maybe I divide by m, so I get s square plus b plus kp over m, s plus ki over m. So I take m common, and maybe I put the m here. Okay, it's alright, I'm putting it here. kps plus ki. So again, I'm comparing only the denominator. As a first order approximation, it means you can find some parameter for kp and ki from which you can start tuning at least. So you know some parameters that give you some value for settling time and peak time close to your requirement, but it's not really exactly equal to your requirement. Because if you want exactly equal to your requirement, you need to compare basic form with some basic form, canonical system with canonical system, higher order system or system with zero, like non-canonical system. We need to use root locus method or some method which we are not dealing with now.
Doctor?
Not now. So now what I'm doing, I'll be comparing both denominator. So then b plus kp over m. So I'll be saying b plus kp over m equal to 2 zeta omega n. And also I'm saying like omega n square equal ki over m. And zeta and omega n I found zeta and omega n from my design requirement. Those are my design requirement. Okay. From them I found zeta and omega n. So now I have omega n, m is given, so I can find my ki. I have zeta and omega n, bm and given, I can find my kp. So then those are my kp and ki, which be as a first starting point from which I can keep tuning later to achieve my design requirement. So we don't start from scratch and keep tuning without knowing how to tune. No, we have a starting point. If your system is non-canonical system, you still be able to compare with canonical system. But in general, for easy system, first or second order canonical system, comparison, it will give you exact value. Any question regarding what I'm saying? Any question? So here he asks the question, will the closed loop system with this controller that we found, Ki and Kp, will have a settling time of 2 seconds and a peak time of 1 second? Yeah, I'm asking you the same question.
No, doctor,
No, why?
because there's a 0 on the numerator.
Denominator. Thank you. So then the answer is no, system will be faster probably and larger overshoot. We are not going into why is he saying that. Later on we'll master everything. Just this example usually I don't give at the beginning, but if system is not canonical, has 0, like this system we had, or higher order system, can use calculation based on canonical system as a starting point. So it's good to have this example to know, like, okay, you can still use calculation based on canonical system as a starting point. If possible, also can place dominant 1 or 2 poles if it's higher order system at the desired location, then place other poles to be much faster. If they are faster, so then you can neglect them. You know you are doing closed loop system. So then in yourself you can tune your PI parameters, and your tuning will affect the closed loop pole location. So you can have, if you wish, having some poles far and keeping some other poles near to the imaginary axis. In a way you can have system could be approximated to first or second order system. Often requirements are given as inequalities, and this is we'll see in solving session tomorrow. Like we'll take often requirement settling time as you see here in your project, settling time less than maybe so always as inequality. The requirement given always as inequality, often as inequality. In your project you don't really need to do the calculation as we are doing it here by hand. You can doing them on MATLAB, but you need to verify that you are achieving whatever parameter you choose, you are achieving the design requirement. Here is an example. Plot region in complex plane where poles, okay, let me have it here. Plot, so this question from Prof. Rick Hill, plot region in complex plane where poles of a canonical second order system must be located in order to achieve settling time less than 2 seconds and a peak time less than 1 second. So settling time less than 1 second and settling time less than 2 seconds. Again, what's the question? Plot region in complex plane. So now I have the complex plane. This is my S plane. This is the S plane, real part, imaginary part, imaginary axis, where poles of a canonical second order system, look to the canonical second order system, because this is very accurate. Everything we are doing is for canonical system. We studied the location and so for canonical. If it's higher order system or 0, then you need to approximate if you want to do the analytical study we did before. So then must be located where the pole must be located to achieve settling time less than 2 seconds and a peak time less than 1 second. Yes, Who could help me other than Tariq? Somebody else. Yeah, who would participate?
دكتور هون بنعوض التي بي والتي اس بقيمتهم، يعني التي بي بنعوضها بقيمتها اصغر من 1.
Yes, Shaheen, right? TP.
لا سعد رمضان.
Saad Ramadan. TP. Yeah. So what do you mean by I replace it by what?
Pi over omega d.
Thank you,
Karim.
Karim. Pi over omega d. Then means omega d is more than pi, right? So where is omega d in the imaginary axis? That's omega d. You remember that's omega d, right?
Yes.
هيدي pi.
If you want, I'm using the reference sheet sometimes for you. I mean, if you wish. Where did I put the reference sheet for you? Do I need to download it? Yeah, it is here. So quickly view, rotate anti-clockwise. It's not very, because it's scanned copy. So you see that's omega d. You have it in your slide, like you have the original slide. But here, so this is omega d here, and here is sigma, right? For any, you have any poles has omega d and sigma. If we have a second order system, we say OS equal sigma or minus sigma plus j omega d. So the real part is sigma, imaginary part is omega d. Then here where I should be, omega d more than pi. Sorry, if that's pi, so then my omega d is more than pi. So my pole location will be here. Same if I am here, because it is complex conjugate. Usually the poles for second order system are always complex conjugate. So then I'll be mirror with the x-axis. So here where my pole should be located, yes, Saad, here where my pole should be located to achieve a peak time less than 1 second. Do you all agree with this?
Yes.
Like now, if you pick any pole here in that region, you will find you will be having settling a peak time response of less than 1 second. So what about the settling time? Settling time is 4 over sigma. Then sigma
اكبر من 2 دكتور.
more than 2. So if that's my 2, assuming this is 2, assuming this is my 2, then I should be more than 2. Then all this region is a valid region, right?
دكتور بس لا لازم تكون كمان فوق الباي، يعني هو اللي بالنص ما لازم نحطهم.
Yeah, why?
لأنه كمان it should satisfy إنه تكون over pi بنفس
Very good.
greater than pi بنفس الوقت.
Very good. So then your final region is this region. Okay, so this is the region
Yes.
on which we are interested. So this is the region. So now if you pick any pole in this black zone, if you pick any pole in this black zone, it will have a settling time less than 2 seconds and peak time less than 1 second. Good. So now you can choose arbitrarily the pole. For example, -3. Maybe I choose my pole. Look, I choose my pole S1 2 equal -3, because it's -2, -3 plus minus j uh,
4 مثلا.
4. Yes, 4, because bigger than pi. Then those two poles satisfy your requirement. So then you have, assuming you have your closed loop transfer function, which is a function of kp and ki, as the example we found. Then here the characteristic equation will be s minus s1 s minus s2. So s minus s1 s minus s2 s1 plus, assuming s2 minus. So you can find that second order polynomial, which is the denominator of your desired closed loop poles. Here we call it, if you want, desired characteristic equation. This is the desired characteristic equation, because I desire to have poles here, because you know this pole will satisfy your requirement, which is settling time less than 2 seconds and peak time less than 1 second. So then those are, if you wish, those are your pole those are your pole, which your desired pole. Okay, so those are your desired pole. Then this is desired closed loop characteristic equation. You solve it and you have the closed loop transfer function. You compare this desired characteristic equation with the denominator, which is a function of kp and ki, and you found the kp and ki that give you a settling time of less than 1 second and a peak time of less than 2 seconds. So that's why maybe you have different values than your colleague, because maybe you pick that's your desired pole. Those are your desired closed loop poles. So those we call them. It's good to note, because these terminologies are important. Desired. So those two are my desired closed loop poles. So then, yes, you choose the KPKI. Your desired closed loop poles are different than your colleague desired closed loop pole, but both of you satisfy the requirement, because you are both in this black zone. Good. Any question so far?
Doctor, can you do it in front of us? كملها ولا بقى you will do other examples?
Yeah, we'll do other example, other detailed example. Later on, we'll start example from 0 and do everything until finding the KP and KI.
Okay.
But now just like course. What is the resulting steady state error of this system for a unit ramp reference? Okay, not very organized. So here they're asking about the steady state error for this system. So now you find KP and KI that satisfy your requirement. So maybe this part C, if you want, from the question. Part A was find KP and KI that gave you settling time less than 1 second and peak time less. Yeah. Then once you find your KP and KI, then you do the identification. You find KP and KI. So now you have them. Alright. So then the question now, what is the steady state error? Who could help in finding the steady state error?
دكتور ما عملنا derivation يعني بدك نقول لك بنعمل derivation.
So is there any faster way to go for? So the question is,
Yes, the
you need
system type.
exactly
Yeah, system type
because they need you to find the steady state error for a ramp input. So now my v desired function of time is a ramp. Function of time is a ramp. So what is the steady state error for a ramp system, for an input of ramp system? Let's see the type of that forward loop, which I call it G of S. G of S equal C of S times P of S, equal C of S times P of S, then Kp plus Ki over S times 1 over Ms plus B. Then maybe here I take S common, then I get Kps plus Ki 1 over Ms plus B. So this is S. Okay. So then what's the type of this system?
1.
This is a system of type 1.
So error constant man.
Yeah, what's this system type 1? You don't need to remember by heart. You go to your system type, to the table. For a system of type 1, what's the steady state error? What's the steady state error for a ramp input? 1 over kV, according to the table directly. So it's then my steady state error in this case is 1 over kV. And what's kV? kV is
limit as stands.
for S G of S. For S G of S, then Z G of S, S times S, they go out. This is 0, so I get ending up having Ki over B. So then E of S, which is 1 over kV, then it is B over Ki. So then, yes,
بس بدك هي closed loop.
this is a steady state error for your closed loop system, yes. So now we take the forward loop only, but according
دي هي الفورورد لوب دكتور.
yeah, but
على طول لما تايب ناخد الفورورد.
ناخد الفورورد. According, if you remember, we did the demonstration actually, and we prove it that it's enough to take only the forward loop, but it gives you the steady state error for the closed loop. And this, yeah, it's a good question actually. And this is, of course, we always talk about steady state error if the system is stable. If the system is not stable, we cannot talk about steady state phase. Okay. If stable, then. So see, then first we found Kp and Ki. Then we ask ourselves, is this controller can give me, can cancel or eliminate the steady state error for a ramp input? It doesn't eliminate. Is it eliminate the steady state error for step input?
Yes.
Yes, system of type 1 eliminates the steady state error for a step input. Okay. So then this was his question. So the like PI controller can eliminate the steady state error for step input. Alright. So he have B equal 1 and Ki equal 69.3. Okay. So now we start the identification by one. First, he took that system as open loop system, B over S2 plus AS plus B. Oh, where is my whiteboard? Okay. So let's now starting with that system, my open loop system is B, if I remember, B over S2 plus AS plus B. Okay, so my open loop system is B over S2 plus AS plus B. This is your open loop system. So assuming, okay, I have then canonical second order system. This is my open loop. So it could be any transfer function which has a canonical second order system. It has no zero. Then, so in the form, it has the form, if you want, omega n square over S2 plus 2 zeta omega n s plus omega n square. So the basic form. Then here I have a controller, C of S, which is, this is my plant, of course, P of S. And output, then my reference plus minus. Let's see what he named. They name them Y and R. So the output they call it Y. And the reference is R of S. Then if you want to find the closed loop transfer function, so you have C forward C B S2 plus AS plus B over forward over 1 plus loop, right? So you'll end up having that equation, that closed loop transfer function. Okay. This will be your closed loop transfer function. Is easy, like nothing, just a derivation. So now, once you have the closed loop transfer function, let's study different scenario. First scenario, when C of S equal P. That's what he's saying. When, so C of S equal to P, or if you want KP, like proportional, just it's equal to, here I replace it by proportional controller. Okay. If that's the case, putting C of S equal Kp, then just replace C by Kp, and then what you do, this is your closed loop transfer function. Okay, this is your closed loop transfer function now. It is if the controller, it's only proportional controller, then your closed loop transfer function y over r equal Kp bkp over s2 plus as plus b 1 plus kp. Okay, this is if I want to compare it with a canonical second order system, so which is omega n square over s2 plus 2 zeta omega ns plus omega n square. See if able to compare, if able to do this comparison, this b plus bkp. Okay, again, as first order approximation, we don't have exactly same denominator here and here, but I can still, as first order approximation, which will give you a starting point for kp that satisfy your requirement. So then what you are doing, you are comparing your closed loop transfer function. Okay, closed loop transfer function, you are doing system identification with your desired closed loop transfer function, desired Yes, desired closed loop transfer function. Desired. That's my desired closed loop transfer function. I desire to have a closed loop transfer function that gave me zeta equal tel value and omega n equal tel value, some values that I know, and thus I derive them from my system requirement, from my design requirement, settling time, overshoot, and so on. I can find zeta and omega n, and this becomes my desired closed loop transfer function. So at the end, you know, your open loop, this is your open loop. It could have, yes, Iyad, it could have, maybe it could have poles here, and then the closed loop, maybe you desire a system that give you a poles maybe here, right? So if that's the case, so you are doing pole placement, you are shifting your pole, you are shifting the dynamic of the system by adding a controller from this location to this location, so make them maybe faster but more oscillate, they oscillate more. We know how the location affect the dynamic of the system. Location of poles affect the dynamic of the system. So this is my desired closed loop. These are my desired poles. These are my open loop pole. Assuming just open loop pole. Open loop poles. Okay. Open loop pole. Yeah. So then you do the comparison with the first order approximation starting point. How to compare then your A equal to 2 zeta omega n and B 1 plus kp equal to omega n square. So I have omega n square, I can directly find kp.
بس دكتور
Yes.
B into 1 plus KP منا مثل النيوميريتور.
Yeah, I told you like just this is in this case also you need to do first order approximation.
Oh, okay.
And it's gonna be your kp starting point. Then later on you go and check if your response really verify your requirement or you need to tune it slightly, little bit more, little bit less, but you have starting point for your system. Okay, then you can find omega n. Actually it's the same, right? Omega n equals this, then you can find your kp. You can find your kp. Here he mentioned something like, which is good also to know, like here in this particular system, when if you decide you have a second order system, you want to have only proportional controller. If you decide to have for a second order system only proportional controller, then you cannot set omega n and zeta independently. You cannot set omega n and zeta independently. Why my mouse not working? Yes, you cannot set omega n and zeta independently, means you have only 1 degree of freedom here. Did you get this message?
أنا ما فهمتها
Yeah.
صراحة.
If you have a second order system and you decide to design for it a controller only proportional controller, then you'll end up having this relation. So assuming you desire, your requirement is to achieve a value of zeta of omega n and another value for zeta. That's your desired pole, that give you your desired pole, because desired pole came from this characteristic equation here. Okay, so you have desired zeta and desired omega n that reflect your desired pole location, which is at the end it's your desired dynamic response. So then, if you have a desired omega n and zeta, and you want to design a system with only Kp, a controller with only Kp, then this Kp will set omega n for you, but
Okay,
doesn't set zeta, because omega n also will affect zeta, so they are related. So then you have 1 degree of freedom here. You don't have, as we saw maybe in I didn't do the derivation, maybe. So here you have 1 degree of freedom because they are dependent of each other. It's not like here, for example. Like here you have Kp, Ki, and actually I did it right. We did it together. Let's go for it back. Yeah, you see here, for example, here you design PI controller, then you can set independently omega n and zeta. Like saying, if I fix my Kp, this will give me omega n. Okay, then if I fix, so you have zeta and omega n. Here you have 2 degree of freedom, because zeta omega n, two equation with two unknowns, they give you Ki and Kp. So you can choose any desired omega n and zeta. You see this is different than the other one, right? This is 2 degree. You have 2 degree of freedom if you want.
دكتور مش الحال.
Like assuming you have some value here for your omega n, and you have a value here for zeta omega n, then you can find Kp and Ki. But in the other one, you have Kp and it's dependent on omega and zeta as well. So you cannot set independently your omega and your zeta and omega n. If you set omega n, you are limited by the choice of zeta. If you set zeta, you are limited by the choice of omega n. That's why it's 1 degree of freedom. So then, yeah, P controller maybe for a second order system is not a good choice. Good.
طب ليه انه حتى لو 1 degree of freedom شو الغلط؟
It's not wrong, but just you limit your choice. We'll see later on more exercises. You will understand. We'll even go back to this thing again. Don't worry. Control effort is proportional to the amount of error. Yeah, well, here I was talking about it. Here just defining the control effort. What is the control effort? Proportional to the amount of error. That's a P controller. Usually C equal Kp times error. So it's proportional to the amount of error. If you increase Kp, your control signal, your error signal will increase. What about PD? So now you do, if you want the calculation yourself, but now having PD طارق. So if I have PD controller, that's my PD controller, then I replace C here by Kp plus KDS. Simply I'm replacing C by Kp plus KDS. Later on I regroup S together, and then here my denominator as first order approximation also. I can compare, this is 2 zeta omega n and this is omega n square. So you can see you have here 2 degree of freedom, right Karim? So here you can set independently omega n and zeta. So you can place your 2 poles anywhere. But in this scenario, you are really limited in where to place your pole, because if you fix zeta, remember always, like the Bible, like how the pole location affect the system. You should know that directly when you draw the S-plane. You should know that this is zeta, this is omega n, and this is omega d, and this is the settling time. So those are things that you need to always remember them. Okay, we spent a lot of time about them at the beginning, right? But it's okay to remember them quickly. So if you have S plane directly, this is mean settling time. Here it means settling time. This represents the settling time. So any poles here, all they give you same settling time. If your poles are here, so then same for example, now omega d. If my any poles are here, all they have same omega d, same damping frequency.
Same peak time.
Very nice. Same peak time. You have same peak time. And if your poles are here, so at the
Same overshoot.
yeah,
Same overshoot.
same overshoot, same z, right? And if your the last one, if your poles are you decide to put your pole like in a way here, any way that follow this trend of this circle, then same omega n. All of those have same omega n, same natural frequency, same oscillation. Okay, so the pole location tells you a lot of things. So now if omega n and zeta are dependent, like so this is the merge for zeta and this is the place for omega n. Okay, so then if you want to choose omega n equal to maybe number 3, case 3, then maybe you are limited in a given zeta. You cannot go in any place, so then you cannot really put your pole. If you decide to have omega n here, so focus with me, if you decide to have omega n here equal to that constant, that value, so because any pole on this thread have same omega n, if you decide to have this omega n, you cannot really go with zeta anywhere, take any zeta. You need to only take only one zeta. So you cannot place your pole in any places you want. So you are limited in the choice where to place your zeta, because omega n depends on zeta. There is a relation between, so omega n is also at the end function of zeta. So if you fix omega n, then you can compute zeta. So then you have a 1 zeta. So that's why here you have 1 degree of freedom. Right? Omega n function of zeta. You see, omega n equal a over 2 zeta. So if you have omega n, then you know that. So that's why it is 1 degree. And how to fix omega n? I fix it by Kp. Me as a designer, I only can control Kp. I change Kp. So when I change Kp, I change my omega n. So then I can tell I want a system with this omega n, or with this omega n, or with this omega n. And directly I imposed zeta in an indirect way, because omega n related to zeta. Becomes clear? So then you cannot place your poles really anywhere you want, if you decide for a second order system to use only proportional carrying. Okay, but if you decide to use PD controller, for example, then you can place your poles anywhere because they are independent. So they told you it's non-canonical system but trans are meaningful. So just like starting from, what about PI? Here's definition of PD. Also, it's good to read the definition. With derivative control, don't have to wait for error to get large before control action become large. That's your controller, C of S. Here is your error, and here is the control action. If it's proportional, you need to wait, assuming you have KP, you need to wait for the error to get large to have a large control action, because it reflects the present. Proportional controller reflects the present, the actual error. He's dealing with the actual error now, how much it is. Based on it, he gives a control signal to the system. But the derivative, you don't need to wait for error to get large before control action becomes large, because derivative, it's the slope, it's predicting. Once you have a trend of going up, so then you have derivative terms predicting the future. So then he will anticipate the error before getting large, because I don't desire to have a large error. If I see my error trending going up a little bit, so I'm doing the slope of it. That's the derivative. So I can predict the future, and I understand so that my future will be high error. So I anticipate it directly. That's the importance of having derivative term. That's why make your system even more stable, contribute to the stability of the system. So then control anticipates the error. The controller anticipates the error if you are using KP plus KDS. Never use D control by itself. Amplify noise. Use it with proportional. Okay. Also, we may saw in MATLAB, we also don't use it this way because physically this is unrealizable, right? It's not a controller that we can realize it. If you do it KP plus KDS. So what we saw in MATLAB is, maybe here, what we saw in MATLAB, from okay, I want to parameter from controller structure. That's what we saw in MATLAB. We see we don't use KDS, like here P, here it's P plus I over S. Usually we say plus DS, but we don't use this way. So how to use, what did we use in MATLAB and your Simulink block? We use D S, right? But we use N over S plus N, usually N a large number. So we use it with a filter. This is realizable. So we add on it a filter. This filter will filter the noise, the high frequency noise. This will be, if you know filter, you studied filter somewhere. Did you study filter? Low pass filter and high
Yes, in measurements.
and measure.
Measurements
So
and
then you know a little bit about body diagram. So then, yeah, this is like kind of low pass filter. So this is frequency, if you want, and this amplitude. So then it filters the frequency which are higher than this frequency, okay, which is related to n. So then we add a filter on it. Okay, so that's how in practice we use. So we don't have degree of numerator more than degree of denominator, physically speaking. So this is, and because it amplifies the noise, so this filter, it helps amplifying the noise. It helps reducing the noise. Also, maybe we may see it in this form. You may see it in this form as well. In this form, like, again, your controller is Kp plus Ki over S plus Kds. Okay, then multiply by 1 over Ts, okay, Tf they call it, but it's alright, T S plus 1 over Ts plus 1. This is also a filter. So it's actually same as the one in Simulink. Nothing different. It's the same. So in Simulink, you remember you have ds n over s plus n. This and this are the same. So here, if I take n common factor here, so I'll get 1 over n s plus 1. If you take n common factor, then n with n they go. So you're still having ds 1 over n s plus 1. So that's the d, that's the s, and this 1 over n is your tf. So n large, tf usually small, a time constant. Okay, it's a filter, it's a first order filter. Okay, so we use it with filter in practice. Then you may ask, when you did PID controller in your Moodle, when I ask you to, and this will comment on it later on some other time, I'll be commenting on your videos. Not necessary those are 5-minute resume. They are not necessary good answer. Even I put some wrong answer actually. So I'll pick them and comment on some of them later on. Yeah, you may ask yourself, when you read it, you was using PID library, but where is the filter in that derivative? You're just tuning, yeah. But actually, if you go inside the library, as I recommend to you, you will see they are using filter on the derivative term. You will see later on they are using on the integral term something we call it wind up. So they are doing all of this for you. But maybe yourself as control engineer, you just need to understand them, but maybe improve the library and provide to the community even better library. Okay. For PID, or maybe you need to change the library for your own use. You need to put 2 controller in cascade, in series, together. You can still tune it from outside, call it many times, but maybe you don't need to use PID at all. You need to design different type of controller. Okay, so then you need to be able to understand the control theory behind and how to design your own controller, and how many you have different type of controller you can do other than PID. But PID is the most used. Any system could be controlled using PID with some limitation. So performance in performance, some limitation in performance. Okay. Just for PI. So what's PI? PI by definition is it's Kp. Okay, Kp plus Ki over S. The control effort gets larger as the error is accumulated. But that's the error, that's the integral term, is the summation of error. We are doing summation of error. That's your C of S, and here is the error, and here is your control signal. Then your control signal gets larger as you are accumulating a lot of error. You sum of them, then after some times you have a lot of error. So that's explain why the integral term eliminates the steady state error. So imagine that's my step input, and I want to track it. So if you have only P controller, maybe you reach something like that. Okay, but if you add I controller, the I, what it will do, they will add this error together. After some time, this summation will be a big quantity, because you are multiplying a coefficient by this big summation. So your control effort will increase. When your control effort will increase, so you will increase the response of the system, because you increase your control effort. Then you may have maybe no error. So that's why the I controller eliminates the steady state error for a step input. Now later on, if it's a ramp, we did the study. Okay, but that's the philosophy behind the integral term. And integral term look to the past. Okay, do the summation of error. The derivative, as we saw, predicts the future because you have slope. If he saw like maybe the error will go up, he directly he computes the slope and he will anticipate for it. You will anticipate for error, so then your error doesn't go up very high because he's predicting the future. That's the derivative term. Integral, looking to the past, do the summation of error, and the proportional, looking to the actual error as it is now in the present. Okay, they did the same. They replaced C by Kp plus Ki over S, and they get this closed loop transfer function, and as first order approximation as well. But this is a this is a third order system. Okay, so then how to do? You cannot do this way. You cannot use canonical relation because third order with a zero also. But he's still saying, but tends to make system slower and more oscillatory. We can know that the integral term contribute to the stability in a sense, like it becomes unstable. It may be unstable. It may become unstable. So that's why it contribute to it give more oscillation. Adding integral term will lead to more oscillation and make the system slower. Okay, derivative term improves the stability and makes the system faster. You remember when we studied the effect of zero? We studied the effect of zero in open loop. But now we are seeing the effect of zero. Zero is the derivative. So I done just this last word. Zero is the derivative. So then we see the effect of zero in a closed loop system now, not an open loop as we did before, effects of pole and zero in open loop. So now we are closing the loop and we are studying the effects of poles and zero. Poles is like integral term. Zeros is like proportional term. Zero is like derivative term. So then we saw like in a while like derivative term improves the stability in the previous slide, but amplifies the noise, improves the stability of the system. Maybe didn't see it clearly, but yes, the derivative term improves the stability because actually it anticipates the error, and that's how it improves the stability, because it's anticipating the error. So it will decrease the overshoot. If you have overshoot, you know that your error maybe go up too much or so on, like you may have overshoot, it will damp the overshoot, damping derivative. Okay, then it damps your overshoot. So that's why it improves the stability, but also makes the system faster. As we saw in the open loop, it makes your system faster. But we saw in open loop, it increased the overshoot, if you remember. But now, actually, in the closed loop, that zero that you added as a derivative term, it's a zero at the end, it makes the system faster and reduce the overshoot. Reduce the overshoot, so it contributes to the stability of the system, make it better stability. But the integral term makes the system slower because he's looking for the error, so need to compute the error until reaching the settling time, or until reaching the steady state without error. So then it makes the system slower. So then we can understand this and make it more oscillatory. The system will becomes more oscillatory, so it contributes to the stability in negative term. It may happen to your system becomes even unstable. Okay, that's all guys. So you can look to the, but one advantage of the PI is it will cancel or eliminate the steady state error as explained, because summation of error. Okay. So then you can look at it yourself. Yeah, we will continue from here next time. If you have no questions, يعطيكم العافية. Tomorrow we will do solving session and for the exam and related to what we did today.